Next week, yeah, a week from tomorrow. All right, so we're going to work in this section. We're going to work with two models: exponential growth and the equation that we're going to use for exponential growth. We're going to use the same equation for any kind of exponential growth, because our base really doesn't matter. We could change our base if we wanted to. Just to make it easy, y equals a e to the b x. And for exponential growth, b is positive. And if we graphed a graph of exponential growth is always going to look something like this. And this point on our y-axis, if we plug in x equals 0, e to the 0 is 1, so we get the point A1. This is where it's going to cross the y-axis. So this number A tells us what our thing is when x equals 0, time equals 0. And then we're also going to work with exponential decay. Same equation, y equals a e to the b x. But for exponential decay, we're going to say b is negative. So our exponent is negative. And exponential decay is always going to look more or less like this. And we still get the same intercept, because when we plug in x equals 0, that becomes 1, and we still get the point A1. So those are the two kinds of models that we're going to concentrate on today. So I just want to go through a couple of examples of working with the growth and decay models, a couple of different kinds of problems that you might see. All right, so we're good with this part so far. All right, so let's talk first about a population model. Population is exponential growth. So we have this city, and the population in millions. Is given by y equals 1.8 e to the 0.026x. And when x equals 0 is the year 1980. And the question is, in what year will the population equal 2.5 million? First off, let me ask this question: what would the population? What is the population in 1980, based on this model? What is it? 1.8 million. So when you plug in x equals 0, that's in 1980. It's 1.8 million. This is our initial amount. So that's where it crosses the axis there. All right. So how would we set this problem up? We want to know when the population is going to be 2.5 million. 2.5 million going to be the y or the x? The y. So we plug that in. Let's plug in 2.5 million for the y. Do I plug in 2.5 million? 2.5, right? Because it says the population in millions. 2.5 equals 1.8 e to the 0.026x. And we know how to solve this, right? What do we do here? Divide by 1.8, get the exponential by itself. exponential function. So when I divide by 1.8, and then I would take the natural log of both sides. So I'm just going to write it as, so that goes away, and I'm going to get 0.26x equals the natural log of 2.5 over 1.8. So I'm just taking the natural log of both sides. And when I get this, finally I solve this, plug this in my calculator, I get x is about 12.6. So what does that tell me? When will the population be? 1992. And then in the last class we were trying to decide what month. So 0.6 years. 0.6 years is about 2/3. A little over half. So sometime in July or August. July maybe. All right, questions on that that example. So pretty easy. We're just plugging in numbers. We end up with an exponential equation. All right, this next one is probably the most involved kind of problem, really, that we've seen probably for the entire chapter. It's not difficult. There's just quite a few steps. All right, so we have a bacteria culture. So we're growing these bacteria in our lab, and after 2 hours, we have the population is 256. After 5 hours, the population equals 541. 541 bacteria. How many? What will the population be? What would the population be 24 hours after we started? So it kind of seems like we don't have a lot to go on here. But we do know, I'm going to tell you that population is exponential growth. So we know our exponential growth equation, y equals a e to the b x. Well, we have two things in this equation that we don't know, a and b. So what do we do here? What is the 2 hours and the population? What is that telling us? Population, is that going to be an x or a y? That's going to be our y. So here's a y. The 2 hours is a x in our equation. So there's an x, and there's a y. So we have 2 points. We have the point 256, and we have the point 541. Well, there's 2 points, 2 unknowns. So we end up having to solve a system of equations. So this is kind of like we did with when we talked about arithmetic and geometric sequences, where we had to solve for our two unknowns in our equation. But we have an exponential equation, so we have a little bit of work to do. So I'm going to write out steps, and we'll do this step by step. So my first step, I'm going to plug in the first set of numbers. And I want to solve for a. So I plug in my first set of numbers and solve for a. So I'm going to write this step here. There's step 1. So my first set of numbers, I get 256 equals a e to the 2x. And to get a by itself, I'm just going to divide both sides of the equation by e to the 2x. So I get a equals 256 divided by e to the 2x. What's another way I can write dividing by e to the 2x? Positive exponent in the denominator is a negative exponent in the numerator. So I'm going to write it like this. So a equals 256 e to the minus 2x. My second step, I'm going to use a with the second set of numbers to find b. So let's do step 2 here. So I'm going to plug in my second set of numbers along with this a. So I get 541 equals, this is a, 256 e to the minus 2x times e to the bx, and sorry, x here is I switched this around. This should be y equals a e to the 2b. X is 2b. So this should be 2b here. And I'm plugging in my second set of numbers, so I get 5b. So 541 equals 256 e to the minus 2b, that's a, times e to the bx, e to the 5b. 5 comes from the 5 hours here. How can I rewrite e to the minus 2b times e to the 5b? What do I do with these exponents? I add them when I'm multiplying two numbers of the same base. So 541 equals 256 e to the 3b. And now I can solve for b. So I divide both sides by 256. So I get e to the 3b equals, I'm just going to write it out as numbers, 541 divided by 256, divided both sides by 256. Take the logarithm of both sides. So 3b equals natural log of 541 over 256, and divide by 3. Plug that in my calculator, and I get that b is about 0.2494. Now we found b. I'm going to plug into my equation for a and find a. Because I have this equation up here that says a equals 256 e to the minus 2b. Well, here's b. So here's going to be my step 3. And finally, I'm going to say, write equation, solve problem. Because we haven't even gotten to the problem yet, we're just finding a and b. So we're going to write our equation and solve the problem. So we need to plug in to find A. So step 3, A equals 256 e to the minus 2 times 0.2494. Plug this into my calculator and calculate. I get A equals 155.4583. So I plug B into this equation. And finally, for step 4, I can write my equation now. Y equals A e to the bx. There's my equation. And the problem asked us to find the population in 24 hours. So there's my equation. So what do I do? What do I do finally to solve the problem? Yeah? Plug in x equals 24. So finally, y equals 155.4583 e to the 0.2494 times 24. And I get that this is about 61819.71. So after 24 hours, we have over 61,000 bacteria. Would my answer be 61819.71? Can I have 0.7 bacteria? Yes? No? No? So would it be 61819.71? Would it be 6181 or 820 or 61819? Would I round up? Would I truncate, or would I leave it? Truncate, because we can't. It has to go up by one, at least one each time. So we chop this off, and I'd say that there would be 61819 bacteria after 24 hours. So that one's about the most involved problem really that we've done for the entire chapter. All right, questions? Yes. The nth term, so our nth term formulas were either for an arithmetic or a geometric sequence. And this one is exponential, so it doesn't quite work that way. It's similar, but not quite exactly the same. All right, so let's talk about radioactive decay. Radioactive decay is exponential decay. So our equation is going to be y equals a e to the bx, where b is less than 0. For radioactive decay, the radioactive materials, they're going to give you a half-life. So depending on the material, each one has a different half-life. The half-life is the time it takes to reduce the amount in half. Yes. Yes. So it's not negative. It's still greater than 0. It's just not negative. Right, right. That's a good question. That was a good question. Because sometimes we said it has to be great. It couldn't be a fraction. We've talked about fractions. Yeah. So yeah, it wasn't negative. All right, so I'll give you a half-life. Time to reduce the amount by a half. That's a time that it takes. If we had started with 5 pounds, we would end up with 2.5 pounds. That would be the time that it took for that to happen. For radioactive decay, A is our initial amount. So when time equals 0, when x equals 0. So it'll tell you you start with a certain amount. And B is the natural log of 0.5 divided by the half-life. And notice the half-life isn't in the natural log. And we would figure out that this is exactly like we would figure this out exactly the same way we did the doubling time, except instead of the doubling time, it's the halving time. So instead of going from our amount to double the amount, we're going from our amount to half the amount. So that's where this 0.5 comes in with the natural log. And with our doubling time, we divided by the interest rate. Here we divide by the half-life. They're kind of related. And this is always going to be true if we use this model for radioactive decay. So I just want to do one example using radioactive decay. So we have radium. Radium-226 is just an isotope of radium, radioactive isotope. It has a half-life of 1,620 years. So after 1,620 years, whatever amount we start with would be reduced by half. If we start with, if our original amount is 5 grams, we want to know how much after 10,000 years. So it's going to keep decaying. All this, the radioactive materials are going to fly off. All the different kinds of radiation that are involved, depending on what kind of isotope this is, and that the stuff that flies off is going to reduce the mass of this piece of radium. We want to know how much is going to be left after 5 years. So this is going to be an exponential decay model. Our equation is going to be y equals our initial amount is 5. E to the b is the natural log of 0.5 divided by 1620 times 10,000. And we just need to calculate this. But I have a question. We said radioactive, kind of related to what Dylan asked earlier. For exponential decay, we said B is negative. Where's our negative sign here? Natural log of 0.5 is negative. So if we look at our graph of a logarithmic function, what is this point? This is the point 1, 0. So over here, between 0 and 1, our logarithmic function is negative. So the natural log of 1/2 is negative. That's where the negative sign comes from. So if you plug it in your calculator, when you calculate this, natural log of 0.5 turns out to be negative, and we get our exponential decay, and this question turns out to be 0.07 grams. So after 10,000 years, there's still going to be a tiny bit of this radium left, and it's still going to be shooting off all this radioactivity. All right, questions there? Okay, I just want to mention briefly another kind of exponential growth. Which is called logistic growth. I'm not going to go into a lot of detail with logistic growth. I just want you guys to be aware of it. Logistic growth is going to look like, and we did some homework problems that involved using logistic growth equation. We just didn't call them logistic growth. So our equation is going to look like this. This is an exponential growth model. Logistic growth, if we graph it, looks like this. And we get a horizontal asymptote up here. And we also have a horizontal asymptote down here. And we call A is called the carrying capacity. So that's the maximum amount that a population could be. And this horizontal asymptote is at y equals A. So that's the maximum amount of our population. So we have population and environment. We talked about the carrying capacity. We saw some problems when we were in chapter 2 that had to do with the carrying capacity and the maximum amount of population of elk or whatever. So we get a horizontal asymptote at y equals A. The population can't grow beyond that amount. So it grows quickly and then it levels off. Levels off because of food supply, might level off because of predators, various other things, but the population doesn't just keep growing and growing and growing. And we end up with an equation that looks like this. And the other constants B and R depend on the situation. And we would treat this just like any other exponential equation, and we would end up having to solve for R or solve for X or something like that. So I just wanted you to have an idea of when people talk about logistic growth, it's a pretty common exponential growth model. All right, questions? All right. Homework. This is 26. And some of these problems are compound interest problems. So a couple of those come back using your compound interest formula, because compound interest is an exponential function. We did a few of those yesterday. We did two examples of those yesterday. So those come back in this section also.